Okay, Mr. Nagy's Physics 11 class, and moving on in our study of dynamics. Again, dynamics has to do with forces. We've looked at a couple of key parts so far in class and on my website, on my YouTube here. We started with just Newton's laws, just a quick recap here. Newton's laws 1, 2, and 3, especially Newton's second law as far as things go, F equals ma. We've talked about gravity to some end, and we talked about friction. So this is our I guess our fourth lesson here, and we're starting to get into the forces that are applied by things like springs. Okay, now we sometimes call this the study of Hooke's law, but named after Robert Hooke, a guy who had a lot to do with a microscope and so on. Those of you who are taking biology. But really, all we're looking at is the tendency that objects have to resist being deformed. Okay, now a spring. I've got a picture of a spring right here. It's got some natural state. The molecules are some distance apart. They've got attractive forces, electric forces, stuff like that. We don't need to go into that. But, I could have a meter stick in class. Same thing. It's got some natural state. And if I apply a force, I'm going to deform it from its natural state. Same thing here with the spring. Now, I can apply a force that would compress this spring. If there's a little bit of space to begin with, I can push at either end, like you can see here. The character pushing both ends of the spring, and what happens is it changes shape. It becomes shorter. It doesn't want to do that, and if you release the thing, it'll probably go back to its normal state. Or I could, hold either end and pull to make the thing longer than it was originally. So again, I've deformed it. Same thing here with a meter stick. If I hold one end against the table and then bend it, it'll change shape. Now, it might not just get longer, it'll actually have a curve to it. There is, of course, an elastic limit. If I push my meter stick too far, it's going to break. If I stretch a spring too far, it's going to stay a different shape. It won't necessarily stay the shape that I've stretched it to, but I can reach what's called an elastic limit. So almost anything is somewhat elastic, a good word to use there, and we're all familiar with elastic bands, pieces of rubber that we use for holding things together and so on. We use metal, which is somewhat elastic, but you need to be aware, as far as engineers are concerned, everything's got some elasticity, some bendability to it. In certain cases, you want it to bend very little. If you're building a bridge, you build it out of concrete, and concrete does bend very little, but they need to take into account, if you're an engineer, how much everything will bend, and especially what the elastic limit is of that particular material. We nowadays, of course, engineer all sorts of materials. Might be familiar with the Olympics last summer. There was a South African runner who qualified and competed. I believe he was a 400 runner, might have run 800 as well. But he's an amputee, and so he's got these lower leg apparatus, which are engineered springs, so to speak. Now, they're not made of metal necessarily, and they're not made of rubber or wood. They're probably made out of some kind of a fiberglass material, and carefully engineered to spring back, to exert a force to get back to their original shape. Here we've got some character. It's a slingshot picture I found online, and he, instead of compressing, like his force of gravity acting on this runner, is compressing these foot springs, if you will. By the way, the person he's running against has also got these. And of course, your bones and tendons and so on in your own foot, if you're not a double or an amputee, have some elasticity of their own. Everything does. So we've seen slingshots like this character stretching out with a tremendous amount of force. He's got something loaded in there. I didn't see in the picture what he's got loaded. Maybe it's paintball or something like that. And so he's exerted a tremendous force that way to stretch. So here's an example of compression, and here's an example of stretching something. And so we're all pretty familiar with how these things work. We've seen them in our day-to-day life. Now, Hooke's law states this: when an object's in a state of equilibrium, when there's no forces acting on it, equilibrium. I shouldn't say no forces. Of course, gravity is acting down on every part of this spring here, but no outside unbalanced force, I guess we might say. If we exert a force, it'll stretch so much. So the length of the stretch here is x when I exert a force. If I exert twice the force, and we might use gravity to exert twice the force. So here I'm putting twice the mass of an object here to exert twice the force. So if this thing here has this mass, this is 2m. So the force of gravity is twice as much, because the force of gravity, of course, is m times 9.8, the gravitational field strength. And what happens is it stretches twice as much if it's a spring that obeys Hooke's law, and if we haven't exceeded the elastic limit. So Hooke's law is pretty straightforward here. F is equal to kx. Now you'll notice in this equation that I found on, again, just off the internet, there's a negative sign. We often put that in there, and force being a vector, direction matters. So why we put the negative sign in is if I exert a force that way, and I call that, I can't see that very well, let's go with yellow. I exert a force that way, and I say that's in the positive direction. The spring will exert a force in the opposite direction, in the negative direction, wanting to return to its original shape. That's what the negative sign is all about here. It's simply the direction the force of the spring is exerted. If this force is positive, then the force the spring is exerting is in the negative direction. That's why the negative sign. I'm sometimes kind of slack on that. I treat this more as a scalar situation than a vector situation. But correctly speaking, force is a vector, and I should have that negative sign on there. K is a spring constant. And I get the spring constant by, maybe I wanted to add 3 forces here and continue this situation, 1, 2, maybe I added a third and a fourth, and we're going to do a lab like this, collect some data, and take force versus the length of the stretch. And when I graph that data, F versus X, it's probably going to be linear. If it's a Hooke's law spring, one that I haven't extended the elastic limit again. And so the slope of this line, the rise over the run, M is equal to delta F over delta X. There's a delta X. And again, sometimes we're slack and we don't put the little deltas in there. So K is equal to F over X. Okay, so K is the spring constant. It's simply the slope of that line. That's it for Hooke's law. Let's do a quick example. Let's consider this runner up here. Let's say he's an 80 kilogram runner. So if the mass of the runner is 80 kilograms and the springs on his, what are we going to call them, an apparatus, and well, we'll call them the feet. The feet, it's lower leg and foot, of course, compress, let's say 3 centimeters. What is the spring constant? Constant K. Okay, quick calculation. So we're taking these apparatuses he's got here. I'm going to draw them out to look like a spring, right? And we've changed the length of this thing, 3 centimeters, and that's 0.03 meters. Centimeters, meters are fine, both of those units, so we've applied a force that way. What force did we use to compress that thing? It was the force of gravity on this guy. F is equal to mg. This guy was 80 kilograms times 9.8. And again, close is good enough. I'm going to round that just in my head. I'm going to multiply it by 10. It was about 800 newtons. Okay? Little subscript G there. It would actually be a little bit less than that, but 80 times 9.8 equals 784, but 800 close enough. So F equals Kx. Notice I left the negative sign off. K is equal to F over X. So it's 800 Newton force. Compress that thing by 0.03 newtons. I've left the units off for neatness as I calculate this. 800 divided by 0.03 is about 2.67 times 10 to the 10 to the fourth newtons per meter. It would have been a fair bit less newtons per centimeter, but that would be the spring constant for this. And we could go and use that and calculate, well, if that's my spring constant, how much force would I get if I compress that thing by 400 newtons? So it's a fairly high spring constant. I know that in the Olympics, there was talk about, and they've had to come up with, because we have runners in the modern Olympics that have these apparatuses, you may gain an advantage from that. So they've had to set limits as to how much springiness, if you will, that these things have. I know there are other situations out there where objects that rely on springiness. I've talked about myself golfing before. A couple of years ago, I had a driver, and the driver I had on the club face, it said not legal for U.S. Golf Association play or something like that. The idea was that how much my club face, when it struck the ball, would deform, and then want to snap back. Mine had too much. It's called a coefficient of restitution. It wanted to snap back with too much force. So I'm going to leave us here with a little video. Okay, so here's a video of a golf ball hitting a surface, and you can see that the surface bends. It's a very slow motion picture. The surface that it's hitting bends back somewhat. That'd be the golf club. And look what happens to the golf ball. But golf balls have a ability. They're very elastic and they bounce back. Remarkable how much it deforms the golf ball, but it does come back to its spherical shape.